So the general context for my talk and for all the stuff that I do is this never-ending story of compromise between accuracy and efficiency in computational chemistry, where we know the fundamental law for most of the applications that we're interested in. That's the electronic Schrödinger equation. And unfortunately, we can't really solve it exactly. And so we have this amazing zoo of methods that make a different compromise between accuracy and efficiency. And as you go to the less accurate and more efficient models and methods, you can treat larger and larger systems. And people are pushing all across this boundary to increase the efficiency and accuracy of the methods. And one important aspect is that specifically in sort of computational chemistry and materialist modeling, they are not really separate, these scales, right? You are typically, if you are interested in targeting certain system sizes, it might happen that you want to parametrize your approximate method by running some more accurate calculations on smaller systems. So this is really a cascade of methods that cooperate often in applications. Now, not all computational chemistry is about electronic structure, but I think it's fair to say that if you do computational chemistry, there is at least, the electronic structure is at least implied somewhere underneath. And so when you're doing electronic structure, when you're solving the electronic structure, you're really doing quantum mechanics for electrons, right? And so you could think of this as two very basic steps. In the first step, you start with some description of your molecule, of your atomic system, and that can be either full structure with coordinates and atom types of your molecule, or it could be just sort of a molecular graph where you're interested just what is connected, or it could be even some coarse-grained model. And then you construct a Hamiltonian for this molecule in the first step. You pick the Hilbert space, you pick your basis, you write down the Hamiltonian. So that's your first step. And then in the second, you want to solve this Hamiltonian. You want to solve the Schrödinger equation for the Hamiltonian, get the energy and the wave function or any other property that you might be interested that derives from that. And then there are, of course, other steps in the whole world of computational chemistry where you then use these and you might want to run molecular dynamics or that kind of thing. But here I'm interested in the electronic structure problem only. And then on this diagram, you can kind of distinguish two very, very broad classes of methods. In the ab-initio methods, the first step is trivial, right? You just take the ab-initio Hamiltonian from first principles, and that's it. And then what's tricky is the second step where you want to solve that, and you can't do that exactly, so you have to approximate somehow if you want to do it with reasonable efficiency. And this is the world of ab initio methods, couple clusters, quantum Monte Carlo, which we've heard about a lot here. And then the other broad class of methods would be where you make this more complicated, the first step. And so you want to write down some approximate Hamiltonian that best captures the kind of properties that you're interested in for your system, and you have in mind that you want to write it such that it's simpler than the exact one, so that the second step you can then solve exactly, right? So it might sound a bit trivial to solve it exactly, but you can do it, and so then what becomes really the source of approximations in these approaches is how you build the Hamiltonian. And so this would be, for example, density functional theory, where you try to approximate the Kohn-Sham Hamiltonian by defining a functional, or tight binding approaches, or even simpler stuff like Hubbard model. And people have tried since about 10 years ago, I would say, with rapid increase. Well, I mean, people have tried before, I'm sure, but the recent explosion is about 10 years, last decade, where people have tried to put machine learning in various of these steps in order to help solving the electronic structure problem. And so I would say the first kind of efforts were this kind where you try to circumvent the electronic structure problem entirely, right? So you don't want to deal with Hamiltonians at all. You just want to directly predict from the atomic structure the target properties that you're interested in, right? And so these would be machine learning force fields or other predictors of molecular properties. Then in this class of methods, you're trying to learn and predict some effective Hamiltonian. And so this would be machine learned functionals or parametrizations of tight binding Hamiltonians with machine learning. And so in this setup, you don't really have any sort of physical guiding principle, right? Because these are effective Hamiltonians that you're learning. And so you need to typically resort to like regular supervised machine learning. And in this, and then there's this third approach where you try to solve this other step. So you have given Hamiltonian. So that's not the part of the problem here. So you have a given Hamiltonian, and you just try to solve it, and you want to use machine learning to help with that. And so here you would typically represent the wave function with a machine learning model and use the variational principle. And so this is so of these three, it's going to be the third one that I'll be talking about. And so for many people here, this slide might be a bit boring, but I'm sure not everyone here has run quantum Monte Carlo calculations. So I'll just review the math that's involved in this. And one of the points here is that quantum Monte Carlo, variational quantum Monte Carlo is very simple framework. And so it's super easy to actually set up a quantum Monte Carlo calculation, variational quantum Monte Carlo calculation for essentially any Hamiltonian that you might be interested in. And this math is valid for any Hamiltonian, right? And I'll show how it then goes to something more concrete later, but this is independent of the kind of Hamiltonian you have, the basis you have. And so you start with the Schrödinger equation, right? You have the Hamiltonian, you have some states living in a Hilbert space. And then you introduce some basis, that's the x, and that gives you a wave function that is now a regular scalar function that takes the basis states as the input. Then another core ingredient is Monte Carlo integration, right? Where you can replace the expectation value for any operator, but here for the energy, with just an expected value of this quantity, where you are sampling the basis coordinate vectors from just the square of the wave function. Then this local energy, you can simply evaluate as this sort of sum over all the basis vectors of the matrix elements of the Hamiltonian weighted by this fraction. And now notice that if the Hamiltonian is not sparse in this basis, this step might be very costly, right? Because you have to sum over the whole space. So this will be very efficient if you have a very sparse Hamiltonian. And another important property here is that if you have an exact wave function, an exact eigenstate, then this local energy will be actually equal to the eigenvalue energy for any sample, right? So as you go to, as you near the exact state, this sampling becomes actually more and more efficient because the variance goes down. This is a very nice property of quantum Monte Carlo. Then there is the variational principle, which is really just a different way how to formulate the Schrödinger equation, at least for the ground state, where you can just get the energy not by solving the eigenvalue problem, but by minimizing the expectation value over all the possible wave functions. In practice, you would parametrize some sort of ansatz and just minimize over the parameters, and that gives you an upper bound. And then you want to minimize, right? So you probably want gradients of the energy. And it turns out that's also easy to evaluate with sampling. So you just need the local energy that you already have. And then you just have to calculate this gradient of the wave function, or the logarithm of the wave function. And then an expectation value over that gives you the gradient. And finally, you need to sample, right, here. And so that you can do in many different ways. But always you can use Markov chain sampling. It's kind of like a poor man's way how to do sampling. You always take, so you have some walkers, right? And then you generate some proposal moves. you could always use some sort of Gaussian sampling around your current samples, and then you just accept or reject that step with this probability, right? And so you can turn this into a very simple code, and this is how you would then do it in practice. This is written in PyTorch, which is what I use, but I think it can be pretty much followed as a pseudocode. So you have your Hamiltonian, you have your wave function ansatz, you have something that samples from your wave function, and you have your optimizer that does the gradient descent or something fancier. And then what you really do in a loop repeatedly is that you get your samples from your wave function, then you evaluate the wave function ansatz, which in our case will be some sort of neural network. You calculate the local energies, right, which you have to then implement for any particular Hamiltonian, but that's kind of the only thing that is specific to a Hamiltonian. And then you take the gradient and you update the parameters in your wave function ansatz, and you can just run this repeatedly until convergence. And this is actually taken from a working code, so really the only thing you need to then adapt for a new specific Hamiltonian would be the Hamiltonian, specifically how you calculate the local energy. And of course, the ansatz will be probably specifically designed for a given problem.
I remember from learning density, gradient define the direction. Experience that as well, because not all the space is covered with data, so some direction.
I think if it's done formally correctly, then the gradient doesn't have a finite variance, and so you might have outliers that sort of come. Now that is specific though. This depends. I think this is system specific. So for some Hamiltonians, this is not an issue, but for some Hamiltonians, it might. Yeah. But in practice, I think this is. In practice, this will always result just in some numerical outliers that you need to deal with, but isn't like a fundamental problem that would prevent you from doing this in general. At least that's my experience.
So that's empirical fact.
Yeah, right. Okay, and so one more kind of very general thing that again might be. It's probably well known to many people. So if you're dealing with many particle states, which you typically do on electrons, and a molecule is a many particle system, right? Turns out that if these are indistinguishable, like electrons, they either are bosons or fermions. And then it turns out that the states need to be either symmetric or antisymmetric with respect to exchanging particles, right? And in general, there are two ways how to deal with this. In the first quantization, you take as your basis states really sort of assignments of you say, okay, first particle is here, second particle is here, third particle is there. So this is an example when I have 3 particles. And so in this setup, your wave function then needs to be either symmetric or antisymmetric for bosons or fermions. In second quantization, you want to kind of avoid having to deal with antisymmetric and symmetric wave functions. And so you come up with some discrete basis for your particles, right? So here I'll do 5 boxes. And then you just say, how many particles do I have in those boxes, right? So this situation here would kind of translate into this. So you just say, okay, there are 2 particles here, 1 particle here. But you don't say which is which. That's kind of treated in the basis states. And so here your basis states need to deal with the antisymmetry or symmetry. But the wave function itself doesn't have to have any symmetry, right? And so that, of course, in the computational setup then simplifies things. Okay, and so now how does it look in practice? So I'll talk about 2 Hamiltonians. One is the electronic Hamiltonian for molecules, for electrons in molecules. And then I'll talk about a sort of model Hamiltonian for excitons and phonons. But so I'll start with this one. So here when you're considering electrons in a molecule, so this would be water, you have just electron coordinates in a 3D space, right? So you have the total space for the wave function is a 3-dimensional space. And since you're in first quantization, your wave function needs to be, and electrons are fermions, your wave function needs to be antisymmetric. So that's the Hilbert space. And then you have this Hamiltonian. Electron interaction and the electron nucleus. And the given molecule is specified by the charges and the positions. And the only thing that you need now to fully specify the problem and start coding is you need the local energy, right? And that's pretty much just these multiplicative, so that those translate directly here. And this translates into evaluating this fraction, right? So you need to calculate the Laplacian of your wave function at a given position and divide by the wave function. Now, to sort of also connect to what has been said in this workshop before, this is how we would do it in second quantization, right? So you now have to pick the discrete basis, and practically you pick some molecular orbitals that are orthogonal to each other. So some examples here for water. And you say, okay, I have occupation numbers now. So that's, instead of saying where the electrons are, you say which orbitals are occupied. That's your basis now. Because they are fermions, there can be only one electron in a given fermion, up to one electron in a given orbital. And your antisymmetric basis states are these so-called slate determinants, where you just you fill a matrix with orbitals, different orbitals in one direction, different electrons in the other. And then by construction, that is antisymmetric when you swap electrons. And so so these are the basis states, and the wave function is a function now of these occupation numbers, right? And since these are really just integers, typically you would think of these as coefficients, right? So you would typically not write this as a function, but just as a vector that's indexed by this complicated index, but can always just write that as a 1D vector. What becomes a bit more tricky is the local energy, right? And it turns out if you go through all the math, that you just need to sum for a given sort of occupation pattern, right? So for a given slate determinant, you need to sum these expressions over all the all slate determinants that differ from the reference y by up to two sort of exchanges of electrons, right? Two excitations. And these things are some integrals essentially from the ab-initio Hamiltonian integrals over the orbitals, right? So you can pre-calculate these and just store them, and then you just have to do these sums when you evaluate the local energy. And this is what Giuseppe Carlo talked about yesterday. So when you then do this setup and represent this guy with a neural network, that's what he was talking about and refers to as fermionic neural quantum states. But so what I will be talking about is this first quantization setup. And before delving into that, I'll say a few words about spin, just to clarify things. So I kind of pretended up to now that electrons are just fully specified by saying where they are, but they also have a spin, right? So in principle, you have the spatial coordinate, but also the spin coordinate. And so in principle, the full thing is a wave function, which is a function of the spatial and spin coordinates. But because the Hamiltonian has no spin, you can actually sort of pretend or just write down that the spins are fixed, and you can say, okay, I'll have just a spatial wave function where the first n up electrons will be the electrons up, and then the rest will be n down. And then what you only need is antisymmetry within these spin subspaces. So you only need that the wave function is antisymmetric in this with respect to exchange of these guys, and separately with respect to exchange of these guys. But you don't have to enforce any symmetry when you exchange up for down. Turns out that the symmetries, or what happens when you exchange up for down, that then reflects the spin state of the molecule, but you don't have to consider that explicitly. That can be that just labels different electronic states, essentially. That's one way how to look at it.
Is this okay for any observable you want?
As long as that observable doesn't depend on spin. Of course, if it does, then yeah, then you have to consider the spin explicitly. Or like not have to consider, but then you have to deal with it. But if it doesn't, then you always need just the spatial part. Exactly. And assuming you don't consider the more trickier things like spin-orbit coupling and relativity. And then as a result of this, as a result of the fact that the antisymmetry is required only in these blocks, the Slater determinants actually decompose into just simple products of determinants for the individual spin-up, spin-down parts. But in to simplify things, I will then, in the rest, I'll again pretend that there is no spin, so I will just write single determinants for everything, but you can always assume that these are block Slater determinants. Okay, so now how to write down an ansatz for an electronic wave function as a neural network. So there were some first attempts from Han at company, 2019, and there was using a sort of different framework, so they tried to do without determinants, but it wasn't really accurate enough, and so then we came up with one way, and David Powell and company came up with another, and you'll hear about that, I guess, from Matthew Folks tomorrow. But in general, both of these use very similar ideas and just fill in different details. And so the sort of common framework is that you start with this single Slater determinant, and that's your starting point, right? So your first kind of attempt could be you just have these orbitals which are maybe represented by a neural network, and you have n of them, and you have electrons, and you form a matrix and do a determinant, and that's your antisymmetric function. But then you can think, well, I don't really need the individual electrons. I don't really need the structure of just the products of pairwise combination of orbitals and electrons for this thing to be antisymmetric. The only thing I need is that if my neural network outputs the whole matrix, I need that if I swap two electrons, right? So now my neural network outputs a whole matrix that goes into the determinant and takes as an input all the electron coordinates. And the only thing I need for the antisymmetry is that if I swap two electrons, the rows or columns of the matrix swap accordingly, right? And as long as that holds, then the determinant will be antisymmetric with respect to exchange. Then the next step is, okay, you say, well, neural networks might output arbitrary things, and that might make things unstable, at least initially in training. And so you multiply essentially your neural network by some sort of envelope that enforces at least qualitatively the right structure of the wave function, right? And in the fourth step, you say, well, I don't need to use just a single Slater determinant. I can use well, they are not Slater determinants anymore, so just determinant, and I can use a few of them and just do a linear combination, and that will still be antisymmetric, right? And now, before going further, I want to say a few things about that. So this is a map of different ab-initio methods, some of which, or most of which we have heard about here. And essentially, my point is that they usually come from some general frameworks: diffusion Monte Carlo, variational Monte Carlo, selected CI, AFQMC, FCI-QMC, a couple of clusters that, if taken at their full capacity, are exponentially scaling and are in principle exact, right? And then in almost all of these, you can always do some approximations or truncations to bring them to the polynomially scaling regime, right? So you do fixed node approximation, you do phaseless approximation, you truncate couple cluster or selected CI. And my point, and so with variational Monte Carlo specifically, that is in principle exact, but of course it all depends on the ansatz that you use. And so Carla and Troyer had this idea, okay, let's use neural networks because they are known to be powerful approximators. And then whether you do the first quantization version, which Brian talked about 2 days ago, I think, as the neural backflow, or whether you use the neural quantum state that Giuseppe talked about. So you end up with these neural network ansatzes in first or second quantization. And what these methods have in common, at least some of them, fixed node DMC, phaseless FQMC, is that they use these trial ansatzes, right? Which is some slated determinant or more of them. And then you can kind of go back to the exact regime if you just increase the number of determinants in your trial wave function. And so in principle, that takes you back to the exponential regime. And now the question is how quickly you converge, right? How many you need to take and how quickly that blows up before you reach the target level of accuracy that you need. And so in fixed node DMC, people have been able to use up to 1 million determinants now. In phaseless FQMC, I think that the common numbers are, the convergence is typically faster. And so in this context, what I'll be talking about is an attempt at a method that just has a very few number of determinants in this context. And it's not really a property that I can say already has, but this is essentially an aspiration, right? We would like to have a method that hopefully, with making each individual determinant as expressive as possible with a neural network, would require the least amount of determinants, and so would kind of be able to be pushed to larger systems and avoiding this exponential regime for a long time. Okay, so now how our Antithes looks like. So this is just this general formula from 2 slides back for a reminder, and then we essentially make choices for the envelope and for the neural network architecture, and that gives us an ansatz that we call Polynet. And so what are these choices? So for the envelope, we just take molecular orbitals. We either do a Hartree-Fock calculation or a small CF calculation, and we use the orbitals as the envelope for the neural network. Then for the neural network, we split the f into 2 parts. So we use this scalar function that can be then taken out from in front of the determinant, and that's going to be our Jastrow. And we use our backflow. And so the backflow ends up being multiplicative, right? So it multiplies. And initially, I thought that, I should say there are multiple. When people talk about backflow in QMC, typically that's meant to mean that you are sort of updating and coupling the different electron coordinates before you feed them into your molecular orbitals. Then what Brian Clark was talking about, he uses a form where it's an additive, right? So you take your molecular orbital and then you add a neural network to it. And what we have here is a multiplicative form. And for some time, I actually thought that this is kind of just a random choice, but then I think I saw in a paper from David Serpelli that there is some physics background for that can be derived. Am I right about that?
About backflow?
About the fact that the multiplicative form actually has some physics argument behind it.
Okay. I may touch on that tomorrow.
Okay, so that's that choice. And then, as I said before, what you need is that this thing is equivariant with respect to permutations, right? So when you swap electrons, you need rows or columns to swap. And so I'll talk how you do that with a neural network later. Then we use electron configurations, which means that these determinants are not completely independent, but we essentially pick, or not pick, but from a CF calculation or whatever other multi-reference calculation, you will get a bunch of determinants which just pick different orbitals, right? So for my first orbital, I take these orbitals. For my second, I take these, and so they are interrelated. And this is really just doing what is done standardly, right? So you take these basic determinants from a CF calculation, and we just choose to modify individual orbitals rather than independently entries in the individual determinants. And then the final thing is that we build in a little bit of physics in the form of cusp corrections, because we know that we know how the wave function must behave when two particles approach each other, and so we just build that in rather than learning that from the variational principle. And so now what about the neural network? So we really just took something that was already working in a different context and modified it slightly. And we took SNET, which is a graph neural network. And what graph neural networks really are is the simple construct where when you have n objects and you want a function that is equivalent with respect to exchange for those objects, you just start with some hidden vectors, and then you form these messages between each pair of these particles or nodes, whatever they represent. And then you just sum, and that creates an invariant message now, and then you update your nodes. And you do this iteratively, and because you're always doing just equivalent or invariant operations, you kind of propagate the assignment of the particles to the nodes from that you started with, right? So that when you swap the initial vectors, these vectors after a few iterations swap as well, right? And this then scales, because you're always doing it pairwise. This scales quadratically with the no, that's wrong. It scales linearly with the number of edges, right? And so SNET is a particular version of a graph neural network that was initially designed to represent a force field. And so you initialize each node that represents an atom in a molecule with some random vector. Then you form these convolutions from these hidden vectors that are parametrized by just the distances between atoms that are expanded in some basis. These red things, they're just small trainable, either small trainable neural networks or just a random vector that is trainable. Then you just update, and you sum the energies at the end. And so this is something that was working very well for doing force fields, and so we just took that and adapted it slightly for electrons. And so now the nodes don't represent atoms anymore, but they represent electrons. And we kind of made it a bit more expressive by considering separate messages within the network for the same spin and opposite spin, and messages from the nuclei. And that's essentially it. Then at the end, we arrive at some sort of hidden vectors for the electrons, and we use that for the Jastrow and for the backflow. So this is how it looks like combined. So you have your neural network here that has this sort of equivariant iterative block inside, and you feed in the electron coordinates, the nuclear coordinates, and here's your kind of physics fixed part, right? So that's the cusps, that's the Hartree-Fock baseline, which gives you your orbitals, and here we have the backflow and the Jastrow that comes together, and finally get the wave function value. And so then you plug this in back into this, that was maybe too many slides back, but you just plug this into this recipe, and so your wave function is now Polynet. It takes in electron coordinates, which is what you also sample, and the local energy is just this expression with the Laplacian, and otherwise you can run this loop, and that gives you hopefully your converged wave function. And so some of the results that we were able to get, I'll just give you two examples. So this is a linear chain of 10 hydrogen atoms. That was a part of this big benchmark paper. And here we compare against sort of previous variational Monte Carlo calculations that were done for this paper. And so that's these two yellow lines. And this is a single determinant version of VMC. This is a multi-determinant version of a VMC. And the blue lines are a single determinant version of Polynet with backflow. And this line is a multi-determinant version, right? And so you can see that compared to the previous results, we have sort of mostly balanced performance across the dissociation curve as you take your atoms apart. But I should say there are methods that are more accurate. So this compares against VMC calculations. There are other methods that are more accurate that I'm just not putting all. You can find all of them here if you want to. So this really just shows that the ansatz can capture even systems where, yeah, so this is an example of a strongly correlated system that is considered hard in chemistry. And so Polynet can capture that with sufficient accuracy.
Can I ask a question? So this is a case where you could study how the number of determinants depend on the length of the chain, right? Because you know the usual objection to multi-determinants is it's going to go exponentially.
Yeah.
Length of the chain.
Yeah, that's a good point. Yeah, we could do that, and this is reasonably small that it can be done. Yeah, we haven't looked at that, but yeah, it's a good suggestion.
Do you try to put DMC on top of it and see how much more you get out of it?
No, we did not.
One hopes it'll be almost exact because it's a one-dimensional.
Yeah, it's a 1D system, so the DMC result.
It's not exactly 1D, but it's very close to 1D.
Yeah.
DMC is, I think, a couple of inequalities in the middle. Essentially, yeah, very nice.
Yeah. Yeah, I think that the nodal surface in this particular case, once you go to the multi-determinant expansion, should be really accurate. And so when you put the DMC on top of these results, I think you get a really high accuracy.
Which then kind of raises a point about your systematic and quite visible improvement in multi-determinant. You would think that if single determinant with backflow is doing a good job, and you're doing a good job with the Jastrow, you should be seeing very little movement.
So this baseline is what you get without doing backflow. So if you take just the Jastrow, right. And so backflow does most of the job, but then yeah, you can squeeze a little bit more accuracy with going to more determinants.
Yeah, so that would seem to say that the Jastrow is still not perfect.
Yeah. Yeah, no, I mean, it's not saturated. We then have another paper where we kind of try to saturate the network on a different system, and you can really push it to the fixed node sort of limit with the Jastrow. With a backflow that's apparently harder. But for the Jastrow, you can really push it to the fixed node limit, but you just need to use more parameters in your network. And again, how that scales with system size, we just don't know yet. We haven't looked systematically into this issue of essentially of size consistency, right? How should the network size depend on a system size to have size consistent results?
So there is a paper last month which was DMC on top of the Hermann. All right.
Yeah, several people have done it, and in most cases, I would say the results were a bit disappointing. In that, not often when you start with variational Monte Carlo and do DMC, you get a big fraction of the remaining correlation energy. Who did it? Max Wilson did it first, and then we've played with it. And there's a recent paper from the ByteDance group, and they've all done similar things. The ByteDance people say it's doing a lot, but I'm not sure it is really still doing a lot, even in their example. You're gaining, 20% of the missing correlation. That's what we were doing. So I was a bit disappointed by that. This was not in 1D system. Good to know.
Okay, so another example is this problem of calculating the energy barrier associated with this automerization process of cyclobutadiene. And so we originally picked this case because it is the transition state has a strong multi-referential character. And we thought that couple cluster, the regular couple cluster fails for it. But I actually very recently found there was a paper. So we took these reference values for couple cluster from this review. And then a group from the group of Lewis, they recently recalculated the couple cluster results, and it turns out that the ones that we took as a reference were just not converged. And so if you actually do couple clusters properly, you find that it's okay. So, so this is not a case where we are beating couple cluster. Couple cluster is still doing fine here. But nevertheless, this is using Polynet on a non-trivial system with strong multi-referential character.
What kind of couple cluster is that? CCSD parenthesis T or?
Yeah, so this thing here, that's CCSD parenthesis T. And if you do it right, if you converge it, you actually get the right answer, which is around 10 kcal per mole.
So what do you mean by conversion?
Oh, just basis set size.
Basis set or the excitation?
Essentially the amount of diffuse functions that you put in.
Oh, but keeping it CCSD parenthesis T.
Yeah.
Interesting.
So I mean, yeah, it's what makes it kind of tricky is that the barrier energy depends on these diffuse functions way more in this particle system than it's typical, and so.
So one thing I can tell you, like for this, for double zeta and triple zeta, we can get exact full CI answer in that basis set using AFQMC with multi-determinantal.
With diffuse functions?
No, just okay. For a basis set.
Yeah, and that's then you get this wrong answer, unfortunately.
Yeah, so there's some, so the result in that basis set is reasonably good. It's about 8 to 10 kilocal. But in that same basis, full CI result in that basis set is roughly correct. But couple cluster result in that basis set is terrible. So what you're saying is surprising. There's there
might be some cancellation of errors.
Something is happening which is non-trivial.
All right. Okay. Yeah, then, well, so what still holds that this is a tricky system. And yeah, so with the same ansatz that we use for this very different system, we can just get the energy in the right sort of bracket. So I think that the paper that I mentioned, that their best estimate of the barrier is around 9. So we are right around that. And this is still reasonable to calculate. So it's not as fast as DFT or some of your more efficient methods, but you can certainly use this with relative ease. And this scales, as any VMC, this scales, well, not as any VMC. So we are in the regime where this effectively scales cubically for these system sizes, and so you can still push it to larger system relatively, still doable. Okay. I'll skip this because Zeno already had a poster about this, and I'm running out of time. And then I'll go to the other Hamiltonian that I wanted to talk about. So this is an example of an effective Hamiltonian, and it's a Hamiltonian that describes so-called exciton phonon coupling. And so what that is that you just can consider a bunch of harmonic oscillators that are oscillating. That's the blue guys connected by interacting via harmonic potential among themselves. And then you have an excitation, essentially, that's running along the chain and it interacting with these vibrations. And this is a good model for excitons, for electronic excitations that are running around alpha helices. So if you want to do now quantum mechanics for this, the best thing to do is that you do the excitons, the excitations in second quantization, right? So you have the occupation numbers. I'll just consider the case where I can have just one exciton on a side. And then I have, sort of the ab-initio first principles way how to do the harmonic oscillators is just this in first quantization, right? So for each one, you get the displacement along the chain. And so then your wave function is just this function of the occupation number and of the phonons. This is the Hamiltonian. Doesn't really matter that much, the exact form. The only thing that's really relevant for QMC is that you can just plug this into the expressions that I had there before, and you can derive the local energy, and you can just run the same QMC algorithm that you would run for electrons. So the only remaining thing is to say what neural network you use, and here it's really simple, right? So you have just this essentially lattice, so you can just use a plain convolutional neural network, and what you're feeding it is this the occupation number for a given site, feeding in the displacement of the oscillator, just normalized. And then if you're in a finite chain, you probably want to also tell it where the network is on the chain. So you feed in just the position. When you're in a periodic boundary conditions and you just want something translationally invariant, then you just don't plug that in, and then the network is by construction, the ansatz is by construction invariant with respect to translation. And just like for the electrons, right, so I have the neural network here, and just like for the electrons, I want some envelope to kind of enforce a basic shape. So here I'll just use the sort of ground state for the harmonic oscillator, which is a Gaussian, right? And then you run the same QMC like you run for the electrons, and these are the results that you get. So this is how the wave functions look like, the states. So depending on the coupling, on the strength of the coupling between the phonons and excitons, there are two different strengths here. You can kind of get either a very weak interaction where you can see that the exciton, which is located here, doesn't really affect the ground state displacement. So this would represent the distribution of the displacements, right? So this is essentially the Gaussian distribution.
One exciton?
Sorry, yeah.
Just one exciton.
Yeah. So this is like this is singly excited Hilbert subspace. And so you don't really get anything almost. There is some slight displacement, but you just increase the coupling 3 times, and this is very strongly nonlinear, and suddenly the coupling becomes very strong, and you get completely. You can see that the total displacement of the exciton of the vibration is larger than the width of the non-interacting oscillators. And here's a comparison with a different method. So this is now a function of sort of the energy difference of the coupled and non-coupled systems as a function of the coupling strength. And so this line is the coupling to the fourth power, which is a sort of analytical result that you can get asymptotic. And then these smaller dots, that's from a sort of a version of DMRG for the system. And that's done in full second quantization. And you can see how for the larger strengths, it starts to deviate from the line. And that's essentially caused by the fact that you just need to, if you do a full second quantization, even for the oscillators, you just need to cut off the finite basis somewhere. But if you get to these points where the oscillators are just completely displaced, then essentially you would need to increase your basis as you increase your coupling strength to be consistent. And you can't do that really beforehand without knowing what it should be, and so you run into this problem. Whereas when you do it in the real space, then you don't run into this problem. So this is sort of a small example how you can get very accurate results for sort of random Hamiltonian with very little effort with neural networks and QMC. And I'm at the end now. So my main message is that deep variational QMC with deep neural networks is a really powerful framework to solve whatever Hamiltonian you want to solve with pretty good accuracy. And in particular, the electronic QMC with neural networks is pretty active. So we now have, from these original 2 papers that I was mentioning, we now have extensions to periodic systems. We have attempts at making transferable wave functions that apply to multiple different geometries of molecules. We have extensions to excited states, work on potentials and diffusion QMC, and people are working on better architectures. Michael will be talking about that on Friday, I think. And then, but yeah, there are also many open questions, right? So it's compared to conventional methods, like the kind of production level QMC that we've heard about here, it's really expensive. And so if we wanted to scale to the kind of systems that people can do with regular QMC, we are just, we will probably never get there with this kind of approach. And so, but that's kind of also not the point. So far we have really looked more at cases where we can show the potential of the method. We haven't really done proper benchmarking, and we haven't searched for like failure cases. And we don't know about size consistency. There is some, it simply must be that if you use a constant size neural network, then of course it just can't describe arbitrarily large systems with the same accuracy. And then there is very little understanding still about whether the limitations of the methods are in the way how you optimize the ansatz or how you, or its expressivity. But what I kind of hope in long term this could lead to is a kind of black box, very accurate methods for systems with 100+ electrons. That would be good for systems with complex electronic structure, right? Thinking small transition metal complexes and things like that. That's it. Thanks for listening.